All right, so let's look at 9.3, which is talking about the law of cosines now. We use the law of cosines for side, angle, side, and side, side, side scenarios. And if preferred, after you find one of the missing angle measurements, in some cases, you can always go back to using the law of sines because the law of sines tends to work out a little bit easier. As you can see, your law of cosines formulas for your triangles, you have one of three different formulas to use depending on which information you use. Which information you're looking for. So you start out with the simple Pythagorean theorem looking formula, but all of them have -2 times whatever sides are given times cosine of the angle that you're either looking for or the angle that you already have. So you have a squared equals b squared plus c squared minus 2bc cosine a. B squared equals, and you can see the rest of these, but the way to help you remember it, they all look like the Pythagorean theorem. This one side equals the sum of the other two sides, and remember that they also start and end with the same letter. So there's always whatever letter you start with is going to end with minus 2 times the other two sides times cosine of the angle that you started with. So started in with the same letter, they look kind of like the Pythagorean theorem. Now let's start applying it. So it says solve the following triangle. So we have a side angle side situation. So this is perfect for the law of cosines. We just plug it into the formula. So we're given side B and C. So we're looking for side B. So that will be the side that we start with. So we'll have B squared equals, and it's C squared equals A squared plus C squared. So 5 squared plus 6 squared minus 2 times 5 times 6 times cosine of B, which is 25 degrees. So we simplified this out, and we're going to end up taking the square root to get B by itself. So this will be B equals the square root of 25 plus 36. So 61 minus 10 times 6, so 60 cosine of 25. 61 minus 60 cosine of 25. And we need to take the square root of all of this. So the square root of 61 minus 60 cosine 25 gives us 2.573. So B is approximately 2.57. And now we can use the law of sines to find our two missing angles. So we can do sine of 25 degrees over side B equals sine of A over 5. And we can do the same thing with 6 and angle C. Now let's look at another one where we have all three sides. This one is going to be a little bit trickier because it's going to require us to use the inverse function because we're looking for a missing angle measure. So we can start with any of the three sides, but remember, whatever one you start with, that's the letter that you end with. But let's just say C has the largest one, so we'll go with C. Again, it does not matter which one you start with because you don't have any three of the angles in the first place. But we just want to use C. So 8 squared equals 4 squared plus 5 squared minus 2 times 4 times 5 times cosine of angle C. So this will be 64, and we need to subtract these two distances. So we'll do 64 minus 16 minus 25, and that will give us 23 equals 2 times 4 is 8. 8 times 5 is negative 40. So negative 40 cosine C. We divide both sides by negative 40, and we're going to have to take the cosine inverse of both of them. So we have cosine inverse of negative 23 over 40 equals C. So that is approximately 125. And now we have one of our missing angles. We have enough sides, so we can go ahead and use the law of sines to finish solving for the rest of our information. So now we have problem 3, where you just need to draw your triangle. And then problem number 4, again, you draw your triangle. This will be a side angle, side scenario like our first one. So I'll leave those to you guys to practice on your own. Now let's look at a couple of our applications. The first one says a cruise ship maintains a speed of 21 knots, sailing from San Juan to Barbados, a distance of 600 nautical miles. To avoid a tropical storm, the captain heads out of San Juan at a direction of 35 degrees off the direct course going away from the storm to get to Barbados. It maintains its 21 knot speed for 6 hours, and then the path to Barbados becomes clear. So it's asking what angle should it turn to go directly to Barbados. And also, once the turn is made, how long will it take if it's still going at the same 21 knot speed? So first, we need to find some more information about our triangle. So it tells us that it's maintaining the 21 knot speed for 6 hours. So we can calculate what this distance is that it has traveled. So we simply do 21 times 6. That gives us 126. So it travels 126 miles out, 126 nautical miles. So we have side, angle, side, and we're looking for this angle ultimately. But we can use this information to find this side, which we're going to need later anyway, and then we can also figure out what this angle is across from 600. So we're looking for this angle across from 600. Let's label it. Let's say that this is C. For Barbados, we'll put a B. We'll say that this is A. So that makes this side C. 126 is side B. And our side that we're going to find later is side A. And this is 600, maybe a little hard to see. So C equals 600. So let's see. So we can find this side A first. So our formula is A squared equals B squared, which is 126, plus C squared, 600, minus 2 times 126 times 600, cosine of angle A, which is 35 degrees. And then we simplify this one and we solve it. And we end up with 502.02 for this distance. And now we can use our sides to find our angle. And since we're using this triangle, it's going to give us this angle. We can simply subtract 180 to get the angle that it needs to turn through. So we're looking for angle C this time. So we'll start with side C, which is 600 squared. And we plug everything into the formula and solve it. And so here is the work. So plug everything in. You simplify it. Remember to keep your negative sign when you are simplifying this part of the expression in your problems. And then remember to plug in your negative sign when you take the cosine inverse. And remember that the angle that we find here is this angle inside our triangle, but we want to know how should the boat turn, which is the angle on the outside. So that's why we do 180 minus that angle to get what's left over, the 43.28. All right, so our next problem says, suppose a certain baseball diamond is a square that is 70 feet on the side. So first, let's draw our baseball diamond, and it is a square. So we draw it the best that we can. And it is 70 feet all around. 70, 70, 70, 70. The pitching rubber is located 47.5 5 feet from home plate. So this would be in line with home plate. Here is pitching rubber. So this distance is 47.5, and that's away from home plate. And then it says, how far is it from the pitching rubber to first base? Here's the pitching rubber. First base would be just out here. So how far is it from the pitching rubber to first base? If this line is going straight down the center here, we know that this is 45 degrees. So we're looking for this distance, and we have a side, we have an angle, and we have a side. So we can use the law of cosines to calculate this distance here. So let's go ahead and do that. So we end up getting D is approximately 49.54. So this is our distance from the pitching rubber to first base. Now part B asks how far is it from the pitching rubber to second base, which is going to be at the back of the diamond here. So we're going from the pitching rubber, which is already 47.5 feet out, and we're trying to get to second base back here. So since we know that this is an isosceles right triangle because both of these sides are 70, and we started out with a square, so this angle measure is 90 degrees, then this distance is just going to be 70 times the square root of 2, and we only need to subtract 47.5 from it. So the distance from home plate to second base is 70 square root of 2, which is multiplying the side by the square root of 2, and we only need to subtract this distance from it to get the remaining from the pitching rubber to second base. So we're going to do 70 times the square root of 2 minus 47.5 to get the distance from for part B. 70 square root of 2 minus 47.5. So that is 51.49, and that is this full distance. So we need to subtract. Oh, we already did the subtraction. Sorry. So this distance is 51.49. And now we just need to find C. If the pitcher is facing home plate, through what angle does he need to turn to face first base? So the pitcher is here. He just needs to turn. So now we are looking for an angle measure. So again, going back to the full shape, we see that this distance is shorter than the distance here, which means that this should be an acute angle once we compute it. And the reason why this is important is because this angle should be an obtuse angle because you're starting in short and you're going out wide. Because when we have to find our angle here, we're going to be using a side-side angle situation. Because we only have one angle, but we also have two sides that are involved. So we're looking for this angle, and we're going to use the law of sines, but we need to make sure we get an obtuse angle. Otherwise, if we get an acute angle, that's going to be giving us this value up here at the top. So for part C, we're using the law of sines. We're going to do sine of 45 over the side that we already computed, 49.54 equals sine of the angle that we're looking for. Let's just call it A over 70. And again, we want an obtuse angle because if we get an acute angle, that means we're in this triangle at the top. So we'll multiply and take the sine inverse. So we'll do sine inverse of 70 times sine 45 over 49.54. And we'll see if this gives us an obtuse angle. So and it gives us an acute angle. So that means that it's giving us this angle. Because remember, when you have side angle like we have in this case, we are using this side, and this angle. We can get an ambiguous situation. And in this case, we do. We're getting this triangle up here. We want to find this one. So for the angle that we got, we just need to subtract it from 180. And we got 92.37, so that is our angle that we want to turn through. So that angle that we're looking for in part C, in this case, is 92.37.